Welcome to The Explainer. Today, we're looking at a massive infrastructure shift that Elon Musk has been quietly assembling piece by piece for years. We're talking about a fundamental evolution in how we think about the cloud, moving away from terrestrial servers to a true, functioning space data center. The sheer scale of what's being built right over our heads is absolutely staggering, and it's going to completely alter global computing. Okay, let's dive into this.
For years, we've all seen those stories floating around the tech press about plans to put data centers in space. And if you follow this space, they usually come across as pretty breathless and vague, right? They frame the whole concept as just another eccentric sci-fi idea. But the reality isn't science fiction at all. It's a rigorous, incredibly calculated engineering trajectory. SpaceX is actually doing this. They are building out orbital compute right now, just not in the way the headlines or the conspiracy theories imagine.
Section 1. The Space Data Center Myth.
And this brilliantly illustrates the myth we need to bust right out of the gate. When people hear computing in space, they usually picture these giant International Space Station-style structures, right? Just packed with massive traditional server racks humming away in orbit. Well, the problem with that is thermodynamics. In a vacuum, there's no air to carry heat away via convection. So cooling a concentrated hyperscale data center in space is an absolute physical nightmare. Not to mention the astronomical cost of launching hundreds of tons of localized equipment. The reality SpaceX is building is entirely different. Instead of a single giant station, they're relying on distributed modular compute nodes built directly into thousands of individual Starlink satellites.
Section 2. Satellites that actually compute.
This is where the global Starlink communications mesh fundamentally evolves. It isn't just a pipeline moving data from point A to point B anymore. The network is getting the ability to actually think. To really grasp this, we need to understand what orbital compute actually is. We're talking about hardened, radiation-tolerant mini data centers. Think of them ranging anywhere from the size of a pizza box to maybe a mini fridge. Because they're modular and baked directly into individual satellites, they can easily radiate their small heat load right out into the cold vacuum of space without melting down. Plus, you don't need astronauts up there to maintain them, and you totally avoid the single point of failure of a massive dedicated platform. It is an incredibly elegant, cost-saving engineering solution.
550 kilometers, that is the altitude we're talking about here. Now, in the tech world, we constantly talk about edge computing, right? The practice of placing processing power in local city data centers as close to the user as possible to speed things up, rather than relying on some distant centralized server farm. Well, this completely subverts that idea. This is the absolute ultimate in edge computing. But instead of the edge being in a warehouse down the street, the edge is now 550 kilometers straight up above our heads.
Section 3. The Laser Network Advantage.
The true enabling technology making all this orbital compute possible isn't just the space-grade processors. It's the network connecting it all together. This is the real game changer. Starlink satellites communicate using laser interlinks, which forms a global orbital mesh. And the physics behind this are absolutely fascinating. The speed of light in a vacuum is nearly 300,000 kilometers per second. But when you send light through terrestrial glass fiber optics, it actually slows down by about 30%. Add in the delay of bouncing through all those ground-based repeaters, and earthly internet slows down considerably. By shooting lasers in a straight line through the vacuum of space, orbital networks actually beat terrestrial fiber optics on latency over long distances. They literally break the speed limits of earthly internet.
Let's move to an hour and see how this builds into an actual data transaction happening right now. First, a user request shoots straight up from Earth, whether you're hiking on a remote mountain or sitting in the middle of a dense city. Second, it hits the nearest satellite and instantly routes through that laser mesh, bouncing from satellite to satellite until it finds a node with available compute capacity. Third, the data gets processed right there, in orbit. And finally, the result beams straight back down to the user. That entire round trip, we are talking tens of milliseconds. It's this invisible, lightning-fast relay happening entirely above the atmosphere.
Section 4. Inside an orbital node.
So, now that we understand the network, it's time to look at the actual physical hardware being launched into space to make this a reality. 2 tons. That is the massive weight of the upcoming Starlink Generation 3 satellites. These Gen 3 models are enormous compared to the earlier generations, but that massive scale is absolutely critical because it provides the heavy-duty power from larger solar arrays and the thermal headroom necessary to host much heavier, more capable computing payloads. Now, the Falcon 9 rocket couldn't efficiently launch a full constellation of these beasts, but with SpaceX's massive Starship coming online, those mass-to-orbit constraints disappear. They'll be able to launch dozens of these 2-ton machines at a time.
Now, what's really interesting about this slide is the engineering constraints involved if we strip down the anatomy of one of these Gen 3 nodes. Operating in space is brutal. Cosmic rays can literally cause digital bit flips, corrupting your data. So these nodes will likely rely on highly specialized, low-power inference chips, potentially derived from Tesla's Dojo architecture, to maximize efficiency per watt. These chips are then paired with deeply radiation-hardened solid-state drives. Power comes straight from the satellite's expanding solar arrays, heat gets dumped into the void via radiative cooling panels, and because no technician can ever pop up to visit them, the whole system relies on autonomous, self-monitoring failsafes. They are designed to fail gracefully and reboot entirely without human intervention.
Section 5. Real-world use cases.
Let's shift gears from the hardware engineering to the highly strategic, practical applications of an orbital cloud. Because this isn't just a flex of engineering muscle, there are serious strategic needs for this infrastructure. Take global AI inference, for example. Imagine having a uniform latency cloud available anywhere on Earth. A ship in the middle of the Pacific Ocean could run complex AI tasks at the exact same speed as an office in Manhattan, completely bypassing complex terrestrial fiber routes. For military and intelligence, the advantages are just immense. You can physically blow up a terrestrial data center, sure, but how do you attack a distributed mesh of thousands of moving computers? It's infinitely harder to target and far easier to instantly replicate if a single node goes down. And then there's disaster-resilient infrastructure. Think about a massive hurricane wiping out coastal data centers and power grids. An orbital cloud simply doesn't care about Earth's weather. It is completely immune to terrestrial floods, fires, and grid blackouts.
Section 6. The multiplanetary future.
Ultimately, all of these incredibly complex engineering feats tie back to Elon Musk's long-term overarching goal, Mars. Building an internet for another planet is a totally mind-bending concept. To connect worlds, you need way more than just a long-distance radio signal. An interplanetary internet requires compute in orbit, not just on the ground. You cannot beam every single data request from a Mars colony all the way back to Earth and wait up to 40 minutes round trip just for a response. Communicating and surviving effectively between Earth and Mars will absolutely necessitate an orbital compute layer to process, cache, and route massive amounts of data locally. Getting this working flawlessly in a distributed mesh around Earth is the necessary real-world testbed for that exact future.
So the crucial point is separating what is actually confirmed engineering from science fiction speculation. Confirmed right now, the Starlink laser mesh is active. The heavy mass budgets of the Gen 3 satellites are locked in, and the public patents for satellite-based data processing are filed. The speculative pieces that capture our imagination, like giant, fully dedicated orbital cloud regions or massive Mars orbit data centers, well, those aren't imminent. The power and cooling limits of space just don't allow for that right this second. The near-term reality we're actually looking at is much smarter. A highly efficient, distributed compute layer quietly and meticulously built right into the fabric of the Starlink constellation itself.
Which brings us to a final provocative question to wrap up this explainer. When cloud computing moves to orbit, what happens to Earth's infrastructure? Because the first orbital cloud won't look like a giant warehouse floating in space. It'll be totally invisible to most of us. Thousands of satellites quietly running compute tasks above the atmosphere, delivering results at lightning speed entirely detached from the vulnerability of the ground. It marks the moment the cloud literally moves into the sky, fundamentally changing the architecture and the physical footprint of the modern digital world. Think about that the next time you look up. Thanks for joining me on this explainer, and keep questioning what's possible.